So to finish this session, we have Bendegúz, who's going to present is this really refactoring, introducing EquivcheckEr. So let's give him applause.
Thank you. So, hello everyone, my name is Bendegúz, and what I would like to show you is a tool we have been working on with my thesis advisors, Dániel, Horpácsi, and Thompson at Eötvös Loránd University. And the purpose of this tool is to check the correctness of refactorings, or more generally to check any kind of change that was meant to be a refactoring. And it could be either made by hand or by some automated tool. And I will first just briefly describe what a refactoring is. Then I will talk about our motivations for creating the tool. Then I will talk about the tool itself and the properties we would probably like from a tool like this. Then I will just talk about how we implemented the tool and what were the main technical difficulties we faced during the implementation. And after that, I will just briefly conclude. So let's start first by defining what a refactoring is. So refactoring is a kind of program transformation, but with the added constraint that the semantic meaning or the behavior of the program has to remain the same. So the only thing that can change is the structure of the program text itself. And we are usually doing this to improve the structure in some way, and usually so that the programmer can understand easier what the program does. And here you can see a very simple example of a refactoring. It's an example of a function inlining. So what you can see here in the upper half of the slide is that this is the original version of the program. We have 3 different functions. So this f function calls to other functions, the add and sub functions. And what we can basically do here is to just substitute the function definition where the function was originally called. So that's what you can see in the lower half of the slide. So this is the refactored version. And if we basically just substituted the function body. And in this very simple example, it's easy to see that the refactoring itself was in fact correct. But in the case of some trickier or bigger refactoring, it's not always obvious to see that this is the case. And that's exactly the problem with refactorings. They can be a very error-prone process that requires a high level of attention from the programmer, and especially in the case of refactorings that require some deeper level of understanding of the code base itself. And it can be very easy to introduce new bugs during the refactoring itself. So the chance of introducing new bugs can be somewhat mitigated by having good practices and following, having good processes or following good practices, like frequent code reviews. But these also require a lot of time and effort from the programmers, and it's still possible to miss some bugs. So there are also tools that automate the process of the refactoring itself, like Wrangler or Refactorer. But the problem with these kind of tools is that they usually don't support every kind of refactoring, usually the more mechanistic or relatively easier kind of refactorings, like the function inlining I showed you earlier, or renaming variables. And they can also take a lot of control over from the programmer in how the refactoring is done. And the main problem is that if the tool itself is not implemented correctly, so the algorithm that implements this refactoring, then the refactored code can also contain bugs. So our solution to these kind of problems is a tool we've called EquivcheckEr, which is a tool for testing refactorings. Or more generally, it can test any two versions of the same code base. And it does this by comparing these different versions, so the original and the refactored one. And it tries to find any discrepancies in the behavior of these programs. We could also say that it tries to establish the semantic equivalence of these programs. And while running these tests, it also finds, so if it finds that a program behaves differently, then it collects these counterexamples, so we can later use this information to more easily find where the bug was introduced. It also only tests the relevant parts, so we don't have to, or the tests are not run with the whole Erlang application. It also has Git integration, so it knows about your branches and commits, and you can just use those to do the comparison or the testing. And it's important to mention that it's only a testing tool, so there is no any kind of formal verification happening in the background. So it's still possible that we cannot guarantee that if there is an incorrect refactoring, then EquivcheckEr will find it. So here you can see a list of what you would probably like from a tool like this. And the first one is speed. So we'll probably want it to be reasonably fast, so it can be integrated into the development, where it can be used during the development phase. And it's easy to imagine that if a tool like this took not seconds, but like minutes to run, then probably nobody would like to use it. And we could say that it still could be used as part of some continuous integration pipeline, but let's be honest, nobody likes long-running pipelines. And we also wanted the programmer to be able to run these kind of tests locally, so bugs can be found even earlier. It would also be nice if the tool was easy to combine with other kind of tools like IDEs or CI pipelines. So the programmer themselves doesn't have to learn some completely new process just to be able to be more confident in their refactorings. They can just integrate it into their own workflows. But the most important thing is that EquivcheckEr should never give back false positive answers. So it should only report a finding if it's a true positive. And the programmer then doesn't have to later check manually if this is a real bug or just some false positive. And we think that a lot of static and dynamic analysis tools are not used in practice because of the high number of false positives they give back. So the main tool we used, or the main technique we used while implementing the tool is property-based testing, which basically can be thought of as automated unit tests. And the way in which these kind of frameworks or tools work is that you don't have to provide each test case manually. You just have to define some properties you want to hold in your code base, and the framework itself will take care of generating random input that it can test these properties with. And you also have to provide generators for generating this random data, but most of these tools usually have inbuilt generators for the primitive types that the language they are implemented in have. So you can usually just use those. And the property-based testing framework we used was Proper. So here you can see an example of a property like this. So this is for testing the functor law for the list data type, more specifically the identity functor law. And what you can see here is that it reads almost like a statement in predicate logic. So what we want is that for all L's, this L will contain the generated data. You have to also provide the type of this data, so this will be a list of integers. And then we define the property we want. So if we map the identity function over this list of integers, then we should get back the original list. So what should be the property if you wanted to check the correctness of the refactoring? Our first thought would probably be that we could just evaluate the program and compare the output. And just to clarify, by program I don't mean a whole Erlang application, but just like single unit of computation, like a function. And the problem with this approach is that it doesn't take into consideration the fact that Erlang functions can have side effects and like input, output, or exceptions. And it also doesn't count for the fact that functions usually expect some kind of context or environment that they expect or that they want to run in. And if we don't somehow simulate this context, then we will just get a bunch of runtime errors, and that will tell us nothing about the correctness of the refactoring. So what we did for side effects is that we are basically capturing them. And you can see here how we handled each case. So in the case of exceptions, it was relatively straightforward. We are just wrapping the function evaluation itself into a try-catch block. And if any exceptions are thrown, then we are just using that as the return value. For outputs, it was a bit more involved. But what we are doing is that we're capturing any request for writing to the standard output. We are unwrapping them, so we get the exact string that was meant to be written to the standard output. And we are collecting them inside a list that we can do the comparison on later. And the way in which the Erlang runtime works is that there is another separate actor for handling this kind of requests, so any input and output requests. And the nice thing about this is that you can just implement or just provide your own implementation for this actor. And that's exactly what we did. So we have our own implementation that we substituted that just gets these requests, it unwraps them, and it sends back the string that was meant to be written to the standard output to another actor that will do the comparison later. So for inputs, what we are doing is that we are stopping the evaluation when an input is requested, and we are also sending back a value that indicates this. And we had to do this because it's just we could just generate random byte streams, but the chance of actually hitting upon something that's a valid input is just too low. So this would need some more deeper analysis that could be like this could be this could be the topic of some further work. So we also had to somehow simulate the context that these functions expect. And usually Erlang applications consist of multiple actors that are communicating with message passing. And each actor has their own mailbox. So if we wanted to somehow isolate this kind of, or these functions, then if an actor expected some kind of message, then it would just block until it receives. Yeah, because the way in which this works is that each actor will block until it receives the message that it expects. So we somehow had to fill up the mailbox before we started the program evaluation. And to do this, what we used is parse transform or path transformation, which is basically a way to do some arbitrary modifications of the abstract syntax tree itself before it gets compiled. And what we did is to use parse transformation to transform each receive expression into another expression that will just generate random data. It will send it to itself, and then it will try to read from the mailbox. So basically each actor will just send a bunch of random data to itself, and then we can guarantee that the mailbox will be filled before it tries to receive from it. We also wanted to capture any messages that are sent, and for this we used parse transformation in a similar way. So we are just transforming any send expression into another expression that just tries to print the same text to the standard output. And as I showed you earlier, we are already capturing these kind of requests, so any message that are sent will be just captured along those, and then later can be compared. So here you can see the property we used. So what we want is that for all x's, these x's will contain the function arguments that we are currently evaluating. We also have to provide the type. This will be the type of the arguments. I will tell you how we determine this type later. But we also had this prop same type, prop same result function that basically represents the property we wanted, and it gets two separate or two references to two separate Erlang nodes or Erlang runtimes. One will be used to evaluate the original version and one the refactored one. It also gets the module, a function name, and the generated arguments. So this is this prop same result function, and what it basically does is that it calls the function with the generated arguments on each separate node. And it also has a timeout, so if the function would take too much time to run, then we are stopping it. And if any kind of side effects or IO was made before that, we can just compare on those. But what we get back is the return value of these functions and any side effect that was made. So those are the val and IO variables. We also remove any runtime specific data. So for now we are just removing process IDs, and we are doing that because these are unique to the runtime the function is evaluated on, and we don't want any false positives just because of that. And after that we are just using the inbuilt Erlang equivalence operator to compare the results. And this is the eval function, which is basically just captures any side effects. And you can see here that for the function application, we are wrapping it inside a try-catch block. So if any exceptions are thrown during the evaluation, then we will just use that as the return value. Another important question was how we should generate the data. So the way in which the property-based testing frameworks work is that you have to provide the type of the data you want generated. So the framework can choose the right generator. And there is a type called any in Erlang, which is basically Erlang's top type, which means that like any valid Erlang term is contained in it. And we could just use this any to generate like completely random terms. But it should work, but the chance of actually finding anything would be just too low. So we somehow wanted to infer the types to improve the data generation, to choose better generators. And because of the fact that Erlang is dynamically typed, we had to use a tool called Typer, which is a tool specifically made for typing Erlang source code. And the way in which Typer works, as success typing was already mentioned, so it tries to infer the most precise type it can, but if there is just not enough information in the source code itself, then it will generalize, and in the worst case it will just default to any. So the nice thing about Typer is that the programmer themselves can help it infer better types by providing more type annotations in the source code. And because we are using typer, if there are more type annotations in the code, typer will infer better types, then we can use better generators, and there will be a higher chance of actually finding any bugs. So basically, if there are more type annotations, we have more chance of finding bugs. So we also had to think about which parts of the application should be tested. The naive solution here would be just to test the whole application with randomly generated input, but that would be too slow, especially in the case of like larger code bases. And also, let's just imagine that we rename some variable in the local scope of some function deep inside our function or our program, and we couldn't even guarantee that that part would run in this case, and it would just basically be an integration test. So we wanted to somehow limit the scope, and we only needed the smallest part that was in some way affected by this change, the refactoring. And to determine the scope, we used various static analysis tools. So what we did is to first use the standard Unix diff tool to get the exact lines that were changed. Then we parsed the source code to get the abstract syntax tree. And together with the line numbers, we could identify the exact functions that were in some way affected by the change. And these would form the initial set of functions that we had to test. We also used the call graph. So if we found that for some function they behave differently, then we rerun the tests on their callers too. So to conclude, we've made EquivcheckEr, which is a tool for testing the correctness of refactorings. It's an open source tool. You can find the source on GitHub. It's a command line tool, but we also have a prototype editor plugin for Visual Studio Code that we are planning to release in the future. It's also version control aware, or more specifically, it's Git aware, and it's reasonably fast. We found that even in the case of like bigger code bases, it usually didn't take much longer than like 10 seconds to run. And of course, feedbacks and issues on the issue tracker are welcome. And we would also like to thank the Erlang Ecosystem Foundation for their support in this project. And you can find the source code on this link, or you can just use the QR code there. Thank you.
Any questions? Yep.
Did you try it out on some code base, some refactorings that you had, and how did you?
Yeah, we had our own examples, but we also knew about bigger refactoring. So the regex, I think, module was renamed to RE relatively long ago, but the old module was deprecated, so everything that used that module had to like rename or use the new one. And we found some instances of refactorings in the OTP standard library itself that did these kinds of refactorings, and we tried to evaluate it on that, and it found some discrepancies, but unfortunately, or fortunately, just unfortunately for us, all of these kind of functions that were different in their behavior were the caller functions already handled any differences. So it was a correct refactoring in the end.
So I wondered, you're capturing the exceptions and the output Does that mean that the checker only works on deterministic code?
I think it should work on non-deterministic ones, but I would have to think about that. I'm not sure. I'm not confident in answering this question now. Sorry.
Any more questions? Okay, so we finished this session, and we have a coffee break. I was going to say fika in Swedish. So coffee break. We go back in 30 minutes, I think.